Okay, so I would now like to talk about some of the rules for manipulating four vectors. Okay, so first of all, let's look at the four vector. So let me do this. Good. Let's look at the four vector P mu. So this index mu here, so mu, we call it a free index. And what we mean by free index is you can plug a number in. And what numbers could we take? Well, mu could be 0, 1, 2, or 3. So that means P mu is not one quantity, it's actually four quantities. It could be P0, P1, P2, or P3, depending on what choice we make for mu. And if we have, for example, an equation, so P mu equals, I don't know, some function F mu, which is a function of a whole lot of stuff. This is not one equation, it's actually four equations. And you'll get these different four equations by plugging in a value for mu. So the important idea here, is that you can plug a value into a free index, okay? Now, there's other kind of indices that I can have besides free indices. So let me give you an example of that. Let's imagine that I have X alpha up and P alpha down. In this situation, we call alpha a dummy index. Okay, and notice it appears twice. It appears twice, and it appears once as a subscript and once as a superscript. Okay, or you could say it appears once as a covariant tensor and once as a contravariant tensor. Now, you cannot plug a number into a dummy index. Remember, we said by the Einstein summation convention, whenever an index is repeated, once as a superscript and once as a subscript, this is an instruction that we should sum over this index. So x alpha is actually a sum, okay? And what is it? It's x naught p naught plus, it's x naught p naught plus x1 p1 plus x2 p2 plus x3 p3. So the actual alpha index doesn't really matter what you call it, just alpha repeated is an instruction on how to sum. So x alpha p alpha, we could also written as x beta p beta. If you write this out, you'll get exactly the same thing. Or x gamma p gamma. So this is very useful. You can always change the name of a dummy index, and we call this relabeling a dummy index. So you can always relabel, so that means change the name, a dummy index. Okay, so the specific value that you call the specific name for the dummy index just doesn't matter. Good. Okay, now what would happen if, for example, we have something like this, x alpha up, p alpha down, and then a v alpha up, okay? So now I've got this index appearing 3 times. Well, what on earth does this mean? Perhaps I should be summing the first index, which is up, and the second index, which is down. So perhaps this is x naught p naught plus x1 p1 plus x2 p2 plus x3 p3 and a v alpha. I don't know, maybe I should have that, or maybe I should be summing the second pair of indices where I've got one index up and one down. Okay, so this is what I would get. In general, these two quantities are completely different. They're not equal to each other. And I don't even know which one I should take. I've just tried my best to use my Einstein summation convention, which means sum an index up and an index down, but there's no unique answer for this expression. And in fact, it doesn't make sense. So when you see three indices like this is not something that you allow. This is a nonsense. So whenever indices appear more than once, well, indices can appear at most twice. And if they appear two times, one index must be a subscript, or equivalently, we could say a covariant index, and one index must be a superscript, or equivalently, a contravariant index. And that's just because if you have P alpha, both indices up, and you summed, what you get is not Lorentz invariant. You know, if you get both indices downstairs, what you get is not Lorentz invariant. So neither of these you would consider. Anything with, say, three indices is also nonsense. So the thing that would make sense is if an index is repeated once as a subscript and once as a superscript, okay? So that's rubbish, that's rubbish, that's rubbish, that's well-defined. Also, this would be well-defined if I say had P alpha, V alpha, U beta. So that expression would be perfectly okay. There's one free index, that's beta, and the alpha is a dummy index. So in particular, this would also be equal to P gamma, V gamma, U beta. This would be true as a tensor equation. You'll notice the free indices on both sides match, and the dummy indices, well, I just don't care what I call the dummy indices. So if I write down any tensor equation, the important thing is that the free indices match. So this, let's say P mu, and then let's have Q alpha plus M squared, I don't know, V mu is equal to naught. This, I would say, is a good equation, okay? It's a good four-vector equation. The indices, the free indices mu match. And when I say it's a good equation, what do I mean? I mean that that equation would be the same in every single Lorentz frame. So that could be an equation about nature and not about some specific Lorentz frame that we are working in. Good. If I had something like, I don't know, T mu, Q nu, P gamma, plus H mu, S nu is equal to 0. This is a bad equation. Can you see why? So this is a nonsense. Why? Well, it's a nonsense because of the P gamma. Both of those indices are down. If, by contrast to this, I had T mu up, Q nu up, P gamma down, P gamma up, plus H mu up, S nu up equal to 0, this would be a good equation. Okay, so this is a good equation. Good equation, that means it would be the same in all different Lorentz frames. Good. Okay. One last thing I want you to do, so I want you to try to do a calculation now. Let's take x mu to be t, x, y, z. So that's the contravariant vector. Now let's look at the covariant vector. So what would the covariant vector be? Well, it'll be t then minus x, minus y, minus z. Let's also introduce the energy momentum 4 vector. So it'll be E, it'll be the X component of momentum, the Y component of momentum, the Z component of momentum, and the covariant energy momentum tensor would be E minus Px minus Py and minus Pz. If I decide to study the quantity X alpha, P alpha, there's one dummy index, so no free indices. So this is actually just a number, okay? So work out what it is. And what I want you to verify is that this is equal to X alpha down, P alpha up, okay? And the statement is, what is this rule? We're saying we can seesaw dummy indices, okay? And if you're not a native English speaker, perhaps the name is not very familiar, so let me just explain that to you. If you go to a park where children play, one of the things that you often see in the park, well, it's this metal bar, and it is supported at the middle so that it can swing about the midpoint. Then one child sits on the one side, another child sits on the other side, and when this child goes down, this child goes up, and that motion we call seesawing. This object is called a seesaw, and we say the children are seesawing. Now, where does the name come from in the indices? Well, you can see that this index has gone down, and this index has gone up to go from between the left and right-hand sides. So we say that we have seesawed the indices. That's just a name. I wanted to explain to you where the name comes from, but there's no physics there. So don't worry too much about the name.